Welcome back. In the previous lecture, we established the properties of the two sets of Pauli operators of a qubit pair. In this lecture, we use this machinery for setting up and solving Heisenberg's equation of motion. So here are the equations of motion that we found. A component of sigma 1 has a time derivative which is a component of sigma 1 cross sigma 2. Same for sigma 2, except that there is the opposite sign. And so from that we have already concluded that the component of sigma 1 plus sigma 2 is equal to 0, which is to say that sigma 1 at time t plus sigma 2 at time t is equal to sigma 1 at time 0 plus sigma 2 at time 0. It's this operator of sigma 1 plus sigma 2 does not depend on time. So its value at time t is equal to its value at the initial time 0. Then on the right hand side we have components of sigma 1 cross sigma 2. So we also look at the time derivative of sigma 1 cross sigma 2, and that gives us the difference of sigma 1 and sigma 2. So we should supplement this by a statement about the time derivative of the difference of sigma 1 and sigma 2. Well, that's just the difference of these two left-hand sides. So we have the difference of the two right-hand sides, and so it's minus 4 times the energy divided by h bar, and then a dot sigma 1 cross sigma 2. So we will go about solving these equations in a short while, but before we do that, let me make a remark here. Sigma 1 plus sigma 2 does not depend on time, so meaning that the sigma 1 plus sigma 2 commutes with the Hamilton operator. So the time derivative is 0, commutator is 0. And that's sort of obvious if we notice that sigma 1 plus sigma 2 squared is essentially sigma 1 dot sigma 2. So let's work this out. Sigma 1 dot sigma 2, that's sigma 1 dot sigma 1 plus sigma 2 dot sigma 2, and then sigma 1 dot sigma 2 and sigma 2 dot sigma 1, but they commute, so this is just 2 times sigma 1 dot sigma 2. It's just like squaring a plus b, and you get a squared plus b squared and 2ab. Now the sigma 1 dot sigma 1, we have seen that before, that's 3 times the identity. This is 3 times the identity. So we have 6 times the identity plus 2 times sigma 1 dot sigma 2. So yes, I can also think of the Hamilton operator not to be the energy times sigma 1 dot sigma 2, but an expression that involves the sigma 1 dot sigma 2, because the sigma 1 plus sigma 2 squared, because the sigma 1 dot sigma 2 that appears in the Hamilton operator is simply half of sigma 1 plus sigma 2 squared minus 3. So once we have seen that, it is not a surprise at all that sigma 1 plus sigma 2 does not depend on time, because sigma 1 plus sigma 2 is just an ingredient in the Hamilton operator itself. Right. So, but now let's focus on the expression that we have over here. So there's the time derivative of a function of time is equal to another function of time times a constant. So the structure of this equation is the time derivative of some function of time is equal to some constant, let me call that omega, and then another function of time. And the time derivative of this second function of time is negative the same constant, the first function of time. So we have actually seen this type of equation before, and then we were looking at A plus IB to solve it, but we don't have to go through that machinery again. We can just write down the solution as A of t is cosine omega t, A at 0 plus sine omega t, B at 0, and B at time t is cosine omega t, B at 0 minus sine omega t, A at 0, where we have made sure that at time equals 0, where the cosine is 1 and the sine is 0, we have A at 0 equals A of 0, B of 0 equals B of 0. And you can verify in a simple way by just differentiating. Let's look, for example, at the first one. We differentiate A of t. The cosine omega t turns into negative omega sine omega t. The negative sine omega t is here, and the omega is there. The sine omega t we differentiate gives us omega cosine omega t. Cosine omega t is here, and the factor of omega t is here. And likewise, when we differentiate B of t, we do get negative A of t. So this is the structure of the equations that we have here, with omega equals 4 times the energy divided by h bar. Now that's interesting, because what this says is that 4 times the energy is h bar omega, and 4 times E is the difference between these eigenvalues here. So if we sketch for ourselves an energy diagram where we indicate the energies, eigenvalues of this Hamilton operator, then we have energy E 3 times, so there are 3 states with energy E, and there's an energy negative 3E, somewhere here is energy 0, negative 3E, where we have 1 state. So there's 3 states that have energy E, 1 state that has energy negative 3E. The energy gap between the two is 4E. And when we were talking about the 2-level atom, we call the energy difference h bar omega. That's exactly what this equation says. So we can just agree on writing h bar omega divided by 4 for the energy to begin with, then the difference between the eigenvalues of the Hamilton operator, there are only 2 eigenvalues here, so in that respect it's very similar to a 2-level atom, except that the excited state is degenerate. There's 3 of these excited states, and there's one ground state if we choose E to be positive. So this minus 3E is a negative energy, and the positive E is a positive energy. Then this would be the ground state. We would have 3 excited states with the same energy. And so, except for the degeneracy, it's similar to the 2-level atom that we talked about before, where we call the energy difference h bar omega. So this h bar omega energy difference appears here with the omega as the coefficient that appears in these coupled equations of motion. So now we are all ready to write down the solution for sigma 1 at time t and sigma 2 at time t. So we know the solutions of these equations, and in particular there is the statement that sigma 1 minus sigma 2, that component is equal to cosine of omega t, this is omega, times A dot sigma 1 at time 0 minus sigma 2 at time 0, negative sine omega t, and then A dot, and here's the second operator, sigma 1 at 0 cross sigma 2 at 0. Now this refers to a particular component, but it's the same component everywhere, so and A is arbitrary, so this has to be true for the vectors themselves. So we have sigma 1 at t minus sigma 2 at t equals the cosine omega t of sigma 1 at 0 minus sigma 2 at 0, and a negative sine omega t, and here we have sigma 1 at 0 cross sigma 2 at 0. So we have the difference of sigma 1 and sigma 2 at time t expressed in what these operators are at the initial time, and here we have the sum. So clearly now, if I take half the sum of these left-hand sides, I get sigma 1 of t. So half the sum of the left-hand side is equal to half the sum of the right-hand side. So I have sigma 1 at time t equals, there's the sigma 1 at 0 plus the sigma 1 of 0, but multiplied with cosine omega t. So I get 1 plus cosine omega t. I divide that by 2. I have 1 plus cosine omega t. I divide this by 2. Sigma 1 at 0. Now for sigma 2, it's 1 minus cosine omega t. So it's plus 1 minus cosine omega t divided by 2 sigma 2 at 0. And then there's no trace of this kind of term here, so we just get this, which we have to add in, but only half of it, half of sine omega t sigma 1 at 0 cross sigma 2 at 0. And this we can simplify a little bit by recognizing that this is the square of the cosine of half omega t. This is the square of the sine of half omega t, and half sine omega t is the cosine at half omega t and the sine of half omega t. So let me just do this, and then we have here the cosine of half omega t squared sigma 1 at 0 plus the sine of half omega t squared sigma 2 at 0. And here we have the product of the cosine at half omega t and the sine at half omega t, multiplying sigma 1 at 0 cross sigma 2 at 0. So this is the solution for sigma 1 at time t. And now, how do we get the solution for sigma 2? Well, of course, we could now take this left-hand side and subtract this left-hand side and divide by 2, and then take this right-hand side and subtract this right-hand side and divide by 2. But the other observation is that we can just interchange the labels of 1 and 2, because interchanging the labels of 1 and 2 makes no difference to the Hamilton operator. So for sigma 2, let me just not copy everything, but if there is sigma 2 here, then this will be sigma 2, this will be sigma 1, and here we will have sigma 2 at 0 cross sigma 1 at 0, or an overall minus sign for this term. So here I copied the solutions that we found of the Heisenberg equations of motions for the components of the sigma 1 vector and the sigma 2 vector. So here is the full sigma 1 vector, the full sigma 2 vector, expressed in terms of what these vectors are at the initial time. And of course you can just check that the sum of the two is constant, because you add the cosine squared and the sine squared here, sine squared plus the cosine squared here, and these two terms cancel. Now, we found these results by an explicit solution of the Heisenberg equations of motion, but there is a different way of going about this. And for that, let's look again at time derivative of some operator f, which would be a function of these sigmas, perhaps a component of sigma 1, perhaps a component of sigma 2, perhaps the sum of the two, perhaps the difference of the two, or the cross bracket of the two, a sum operator, and we just assume for now that there is no parametric time dependence, because that would be artificial here. And so we have 1 over IH bar, and then it's F and the Hamilton operator, the commutator of the two. So let me write this out. So this is 1 over IH bar, F times H, minus 1 over IH bar, H times F. Now, H at time t is equal to H at t equals 0. So this is just H, does not depend on time. So here this says if I take the dot product of sigma 1 and sigma 2 at time t, it will just be the dot product of sigma 1 and sigma 2 at time 0. And of course you see ingredients of this. There is a dot product here, there's a dot product here. Also if you take the dot product of this with this, you get dot products of sigma 1 and sigma 2. I'm not working this out, I leave this as an exercise to the students of this course. What I want to point out, however, is since H itself does not depend on time, there is a formal solution to this expression, which says that F at t is equal to F at 0. And now we have on the right, we have minus I divided by H bar ht. And on the left, we have e to the I divided by h bar t times h. And why is that so? Well, it's important here that the h does not depend on time. So if I take the time derivative for verification, time derivative of this f of t that I have written down here, according to the product rule, there are two terms. One where I differentiate this time dependence and one where I differentiate this time dependence. Let me begin with this term. So I'm differentiating this time dependence. That brings down an h on the left. So there will be an h on the left, and then there will be a factor of I divided by h bar from this exponential function. And the exponential function is reproduced by the differentiation, and then the whole rest is as it is. So this is just f of t. Then, if I differentiate here, the exponential function is reproduced, and Hamilton operator comes down from the chain rule, but it comes down to the right. So we have f of t, Hamilton operator comes down on the right, and from the chain rule, we have an additional minus I divided by h bar, minus I divided by h bar. Well, if rather than multiplying with minus I divide by I, rather than multiplying with I divide by negative I. We see that this is exactly 1 over IH bar, the commutator of f at time t and h, which is Heisenberg's equation of motion. So this expression also tells us what is f at time t if we know f of time 0. However, we need to work out these exponential operators of the Hamilton operator. So how do we do that? Okay, so here this is not so complicated, because after all, we know that the Hamilton operator only has two different eigenvalues, e and negative 3e. So if we take the Hamilton operator, we subtract e, take the Hamilton operator, we add 3e, then this product will be 0. Why is that? Because the Hamilton operator, if it takes on values, it will be one of the eigenvalues. If it takes on the value e, then this factor is 0. If it takes on the value negative 3e, then this second factor will be 0. So, we have this simple equation, meaning that the square of the Hamilton operator, well, let me write this out. The square of the Hamilton operator minus plus 2e times the Hamilton operator minus 3e squared is equal to 0. Well, this says that the square of the Hamilton operator is equal to the negative of these two terms. The square of the Hamilton operator is the identity and the Hamilton operator itself with some numerical coefficient. So this is similar to one of those sigma operators. Any product of sigma's operators is a linear combination that involves the sigma, again with numerical coefficient. So it's very similar to that. Further, if I look at these factors that appear here, and I look at them when the eigenvalue is equal to E, then this factor is 0, and this factor is 4E. So I get 0 times 4E equals 0. If I take the eigenvalue equals negative 3E, then here I have minus 4E, and here I have 0. So this tells me that except for an overall factor, the H plus 3E is the projector on eigenvalue E. So more precisely, the projector for eigenvalue E, the projector for that is a multiple of H plus 3E, but for the projector it should be 1 when I have the eigenvalue E. So I need to divide the H plus 3E by 4E, such that I get 1 whenever E takes on the eigenvalue E. Then it's E plus 3E, 4E divided by 4E, I get 1. And I have to get 0 for the other eigenvalue, which is negative 3E. So if H takes on negative 3E, I just get 0. So the projector for eigenvalue E, that's 3/4 plus 1/4 of Hamilton operator divided by E, or 3/4 plus 1/4 Hamilton operator divided by E is just sigma 1 dot sigma 2. What is the projector for the other eigenvalue? Okay, so that will be a multiple of H minus E, because that has a finite value for this eigenvalue, and this factor is 0. Or more importantly, it has a value which is non-zero for this eigenvalue and 0 for the other eigenvalue. So we have H minus E, and now to make sure that this has the eigenvalue 1 when we insert minus 3E for H, we have to divide by the minus 4E. So what we get is 1/4 minus 1/4 of H divided by E. So we have 1/4 times the identity minus 1/4 of sigma 1 dot sigma 2. Very nice, because first of all, we immediately verify that if I add the two projectors, I get the identity, which is the way it should be. But now we can use these projectors to work out functions of the Hamilton operator. So how does this observation help us? For that, I go back to what was discussed in one of the earlier lectures. If I have an operator A with eigenvalues alpha k and eigenkets ak and eigenbras ak, then which are orthonormal and so forth, then the function of A is given by the sum over k, ak, the function of alpha k, and then the ak bra. So note here that we have eigenvalue, and then these two kets and bras that appear here, the ket-bra product, that's the projector for the eigenvalue. And then over here we have the projector again, But rather than the eigenvalue, we have the function of the eigenvalue. And the same now works for h. So if I have a function of h, then this is equal to the function evaluated for the eigenvalue times the projector for this eigenvalue, which is 3/4 plus 1/4 sigma 1 dot sigma 2, plus the function for the other eigenvalue, which is minus 3e, and then the projector for that, which is 1/4 minus 1/4 sigma 1 dot sigma 2. And so with that, we can easily work out what are these exponential operators that appear here. We are now applying this insight to this particular problem. So I have this unitary operator for time t, which is the e to the minus I divided h bar t times h. And so putting in what we have here, it's e to the negative I divided by h bar, and then the energy times t, and then the energy sigma 1 dot sigma 2, where I don't write a time argument because we know that the product sigma 1 dot sigma 2 does not depend on time. It doesn't matter at which time I evaluate it. I can take it at the initial time 0 or at the final time t. For working out this expression, it will be good to make all operators, the sigma 1 dot sigma 2 in particular, refer to the initial time, because then we know what are the commutation relations. Anyway, here this is just e to the minus, and now for e, let me write 1/4 of h bar omega. So we have minus I divided by 4 omega t, and then sigma 1 dot sigma 2. That is just rewriting this expression that we have here. And now I'm going to make use of this expression here. So first of all, what is the value of this function when the eigenvalue is e? So that is e to the minus I divided by h bar te. And that's going to be multiplied by 3/4 plus 1/4 of sigma 1 dot sigma 2. And then the other case is e to the minus I divided by h bar t, eigenvalue minus 3e, and then 1/4 minus 1/4 sigma 1 dot sigma 2. All right, so we insert once more that the energy is now written as 1/4 of h bar omega. So this is this is the exponential of minus I divided by 4 omega t, and then 3/4 plus 1/4 of sigma 1 dot sigma 2. And here we have plus e to the 3i divided by 4 omega t, and it is 1/4 minus 1/4 of sigma 1 dot sigma 2. And this we can now reorganize by just recognizing that there are terms which do not involve the sigmas, and those are 3/4 of exponential of minus I over 4 omega t, and 1/4 of exponential 3i divided by 4 omega t. So that's this term and this term. And then for the terms that go with sigma 1 dot sigma 2, there's 1/4 here and 1/4 here, so there's a common factor of 1/4, and here we have e to the minus I 1/4 omega t minus e to the 3i 1/4 omega t sigma 1 dot sigma 2. And so we have now managed to write this unitary operator that appears here in terms of, well, the sigma 1 dot sigma 2 combination, which is all that really matters, because that's the Hamilton operator. And as we have seen, any function of the Hamilton operator is just a linear function of the Hamilton operator, so it's a linear function of sigma 1 dot sigma 2. No powers of sigma 1 dot sigma 2 need to be considered. So there's a coefficient here, they can be simplified, rewritten, and so forth as we find it convenient. And then they can be used here to evaluate this right-hand side, making use of these commutation relations and algebraic relations that we have derived for components of sigma 1 and sigma 2, and dot product of sigma 1 and sigma 2, cross product of sigma 1 and sigma 2, and so forth. So when we apply this right-hand side to sigma 1 at 0, then in the end we get the sigma 1 at t, and we find all of this. But I'm not going to go through this calculation, leave it to the watchers as an exercise. In summary, we found the time dependence of the 2-qubit Pauli vector operators by solving their Heisenberg equations of motion. In the next lecture, we look at the quantum particle that moves along a line, which is our first encounter with a continuous quantum degree of freedom.